Okay, so now we're going to do a generator. And this will probably be the last example we do before we have a little break because we're at the 50-minute mark here. So we've got a simple alternator. Yeah, not a generator. We'll do generator next. Alternator. Alternators are important. If you lose your alternator, your car dies. And you're going to know why now because the alternator is useful for supporting a current. So we have this picture. I'll show you it in a second after I read the problem. It's a device that generates an EMF, a voltage. A rectangular loop is rotated with some constant angular speed. So we have some loop of wire where it's rotating. So what's changing in this case? This is the term that's not zero. This term could be zero now for an alternator because dA by dt is changing with time. Because if I take a loop that has a constant B field going through it, right? But I rotate that loop, then the flux is no longer constant because as I change this angle, the area vector is changing, and thus my dot product between my area vector and my flux is not constant. It's changing, and so it changes the flux that way, which was this term from this product rule that I had for Faraday's law. So then we can see a picture of this here. So we've got this brush that helps get the current going from B to A or A to B. And we've got this area vector of this circular coil, not circular, rectangular coil. And then the B field is just this direction. At this moment in time, the flux is zero. But that thing doesn't stay like that. It's always rotating. So it rotates constantly at this constant omega, this angular frequency. And then they say, okay, if the magnetic field is uniform and constant at time t equals 0, phi equals 0, determine the induced EMF. So as you can see here, the induced EMF is not going to be some constant voltage. Now we're talking about sinusoidal voltages. And sinusoidal voltages will produce sinusoidal currents. So this is going to be useful when we're doing like AC circuits because alternating current, that's different than direct current. We have an alternating current. The current direction is not changing. It's alternating with time. We could produce that alternating current with devices like these. So here's the diagram of it. And look, this is kind of a nice picture. They show look at the top. You can barely see that. It looks like a pill, but it's actually representing the loop, the little yellow loop. Look at that. They have a nice little yellow loop, and they show you what the flux looks like and what the EMF looks like in response to the flux. And it looks like it's 90 degrees out of phase, right? One's following the other. We've got one's a sine function and one's a cosine. Who's who? Which one is cosine and which one is sine? Brown one is phi, that's going to be sine, and then the other one's cosine. Basically, 90 degrees out of phase. We can see that the flux through it is changing with time, and so is the EMF. So the connections from each end of the loop to the external circuit are made by means of the end's slip ring. The system is shown at a time when the angle is at 90 degrees. Graph the flux through the loop and the resulting EMF between the terminals A and B, along with the corresponding positions of the loop during one complete rotation. So we're going to look at all that. Okay, so first we're going to find the EMF. So we've got this minus d by dt BA cosine omega t. Okay, so what does this derivative mean here? So we've got to do a little bit of math review for trig and also for calculus, but it's an easy math review. I don't want to quite erase this just yet. I'm going to leave that. I'm just going to work down here, or I'm going to work next to this board. So this is our expression. This is our grand expression for our induced EMF if we have some kind of flux and we want to take the time change with flux. dB by dt gives us our flux, but then we also have a flux coming from the area term. So this term is zero because they said in the problem the B field is constant. So this is just gone. We're actually doing with this term. So we have B dA by dt. And then what's that change in area? Well, we've got that change in area is cosine. So we've got, and it's a minus sign. Sorry, there should be a minus sign in front of both of these, actually. It's not plus. It's minus because there's a minus from here. So minus d by dt minus db by dt a minus b dA by dt. Okay, so then we've got minus b, and then we said it was oscillating. We've got a d by dt. Let's put the d by dt out front. So we've got d by dt, and now we've got a constant b field, so that's not changing. But then we've got to take, so b can come out front of the constant. I always like to take my constants when I'm taking a derivative and bring it out front. So that's going to be equal to minus b and then d by dt of a. But then the a is changing with time. It's changing like a cosine omega t. So we've got minus b d by dt of a cosine omega t. Can everybody read that? Is that clear? Okay, so I have to take the derivative of this. A is still constant, but d by dt of cosine, what's the derivative of cosine? Minus sine. So the minus sign cancels out. So I take the derivative, d by dt of cosine omega t, and I have an omega that comes out front too, because it's not just of t, it's of omega. So d by dt of some function, cosine, if it's just cosine of t, then it's just minus sine of t, but it's cosine omega t. So I have to take what's inside first, comes out in front, omega, and then minus sine, what's inside the parentheses. So I have minus omega sine omega t. That's going to be coming out front. So the minus signs cancel. So then I have b omega a sine omega t. That's going to be my expression. B a omega sine omega t. So that's where that comes from. Okay, so the induced EMF varies sinusoidally with time. When the plane of the loop is perpendicular, phi b reaches its maximum and minimum values. At these times, its instantaneous rate of change is 0, and the voltage, or EMF, is 0. Conversely, EMF reaches its maximum and minimum values when the plane of the loop is parallel to B, and phi b is changing most rapidly. So we note that the induced EMF does not depend on the shape of the loop, but only on its area. So if we made this shape anything we wanted, it doesn't have to be a circular, it'll still work. It could be anything, any shape we want, as long as it's closed and the current can flow freely. So that's how an alternator works. We can use this alternator as a source of EMF in an external circuit by using two slip rings that rotate. And they slide against the stationary contacts called the brushes, which are connected to output terminals A and B. Since the EMF varies sinusoidally, the current that results is an alternating current that also varies sinusoidally in magnitude and direction. And the amplitude of the EMF can be increased by increasing the rotation speed, the field magnitude, or the loop area, or by using more end loops. So any of these variables will increase the EMF. It could be a change in omega, change in area, or change in B. That'll all change the induced EMF or induced voltage.